4,000 years is the exact duration nature requires to fully decompose a single discarded tire. Why have these resilient structures become one of the most significant environmental challenges on the planet? At first glance, a tire appears to be tens of thousands of tires move through a complex logistics network in what functions as a symphony of industrial precision. Heavy vehicle fleets equipped with high-capacity platforms and robust fastening systems operate like vital arteries to ensure the flow of materials. These units connect garages, maintenance centers, and scrapyards to massive processing plants located hundreds of kilometers away. Every single tire is removed from circulation with calculated speed before it can accumulate rainwater and transform into a breeding ground for dangerous diseases. Why is so much effort expended on an object that has been discarded? It seems simple to view these items as mere waste, but in reality, modern engineering identifies a used tire as high-grade urban ore. One can notice how the rubber casings are stacked and secured with immense tension during transport to the facility. This is not just a collection of junk, but a concentrated source of raw materials. Inside each worn-out carcass lies a wealth of resources including elastic natural rubber, resistant synthetic polymers, and textile fibers. Crucially, each unit contains high-quality steel that has reached the end of its first. 120 kilometers per hour is the speed at which a vehicle takes a sharp turn, placing extreme lateral pressure on the wheels. Why does the tire remain firmly seated on the rim under such intense physical stress? It only looks obvious that the rubber holds its shape, but in reality, the structural integrity is maintained by hidden internal components. Deep within the architecture of every tire lie beads, which are rings made of incredibly strong braided steel. These metallic cores act as the primary anchors, ensuring that the rubber does not peel away from the wheel during high-speed maneuvers or heavy loading. But this is just the beginning. In a recycling line, these reinforced steel rings transform from structural necessities into catastrophic hazards for the machinery. If a whole tire enters a standard shredding unit, the braided wires can shatter blades, costing several thousands of dollars, seize drive shafts, and bring the entire factory to a complete standstill. Therefore, the steel must be removed before the rubber can be safely processed. One can notice how the equipment prepares for this specific extraction. The tire is positioned securely within a specialized bead extraction machine. A hydraulic hook, driven by heavy-duty pistons capable of lifting the equivalent weight of several passenger cars, penetrates the sidewall of the rubber. The process is only gaining momentum. At first glance, the extraction seems simple, but it requires the application of immense force with surgical precision. The camera glides along the hydraulic cylinders as they begin to retract, and the equipment gradually increases the tension on the internal steel structure. With the hiss of high-pressure hydraulics and the sound of polymer being stretched to its absolute physical limit, the machine pulls. Everything only gets more complicated as the resistance peaks. The force is so overwhelming that the thick, robust structure of the tire twists, folds, and deforms as if it were made of thin paper. Within a matter of seconds, the steel ring is violently torn from the interior of the rubber casing. One can notice the braided metal snapping free, completely stripped of its surrounding material. It is a mechanical victory where the machine successfully isolates the dangerous metal from the recyclable polymer. The raw rubber is now ready to move to the next processing phase without haste. 2 kilograms of pure carbon steel are recovered from every single truck tire processed at the facility. Why is this specific metal extraction so critical during the initial stage of recycling? It would seem the rubber is the primary focus, but this high-quality steel represents a valuable secondary resource that prevents waste. The metal undergoes compression into dense, heavy bales before being transported to specialized foundries to be reborn as structural construction beams or precision automotive components. One can notice how the remaining rubber casing, now stripped of its internal skeleton and structural rigidity, drops onto the moving conveyor belt. The equipment gradually moves the shapeless mass toward the purification zone. But this is just the beginning. The rubber must pass through specialized washing tunnels where high-pressure water jets strip away decades of accumulated road grime, oils, and embedded stones. This sanitation process is vital because even a single stone hidden within the tread could act as a high-velocity projectile inside the machinery. It only looks obvious to clean the material for aesthetics, but in reality, This step protects the internal blades from catastrophic damage during the next phase. The process is only gaining momentum. Once prepared, the rubber enters the primary crushing chamber, where the mechanical force reaches its peak. One can notice how massive shafts, equipped with blades forged from hardened steel alloys, rotate with a slow and rhythmic precision. Everything only gets more complicated at this stage. The low rotational speed is a deliberate technical requirement. If the blades operated at a higher velocity, the resulting friction would generate enough thermal energy to melt the rubber into a sticky, destructive mass that would seize the entire system. By rotating slowly with devastating torque, the blades slice through the tire, reducing it to irregular chunks roughly the size of a human fist. It gets more complex further on. These fragments descend into secondary crushes, where the mechanical violence becomes significantly more refined and targeted. The equipment gradually grinds the material into small crumbs to maximize surface area. During this secondary reduction, any microscopic remnants of steel wire that escaped the initial extraction are finally separated from the polymer stream. The material transitions into a calm stage as it prepares for final granulation. From here, the transformation moves to the next phase of processing. 1/2 millimeter to 2 millimeters is the precise diameter of the granules emerging from the final stage of mechanical reduction. Why is such a minute grain size required for modern road construction? It would seem that larger fragments could suffice to provide volume, but in reality, the chemical integration with bitumen demands an exact surface area to weight ratio for proper bonding. Powerful magnetic separators act with invisible force to extract the remaining fragments of steel wire from the rubber stream as it travels along the conveyor belt. The camera glides along the discharge chute, where only pure organic material remains after the metal is stripped away. The result of this complex separation is crumb rubber, a substance resembling a dense, uniform black sand. The giant tire has completely vanished, replaced by tons of fine powder that has been sieved and classified with mechanical rigor. One can notice how the dark grains flow through the vibrating screens, but this is just the beginning. At first glance, the crushed rubber appears finished and ready for the mixing plant. In reality, the material is still raw and requires specific thermal preparation before it can face the heat of the asphalt tanks. Everything only gets more complicated when considering the microscopic state of the granules. To an observer, the rubber seems dry, yet on a molecular level, it is covered in a thin film of moisture and microscopic dust. Why is this invisible moisture considered a critical failure point for engineering? If these damp particles were introduced into a tank of boiling bitumen, the trapped water would flash into steam instantly. This reaction would create internal voids and bubbles that weaken the road structure, causing the surface to crack within months of completion. The road would fail under the weight of traffic before the inaugural season could even conclude. Therefore, to prevent this structural catastrophe, the granules are transported into a colossal rotary dryer for moisture removal. The equipment gradually rotates the material inside a steel cylinder that is mounted at a slight incline to ensure a continuous gravitational flow. Industrial burners fueled by natural gas inundate the interior of the drum with a constant stream of hot air. The temperature inside the rotating chamber rises steadily as the blades rotate ceaselessly to tumble the rubber grains through the heat. The process is only gaining momentum as the moisture evaporates completely, leaving the rubber in a state of absolute dryness. Transition to the next level of the thermal cycle begins as the material reaches its target temperature. 93 to 127 degrees Celsius is the precise thermal range maintained within the drying chamber. Why is such a narrow temperature window strictly enforced for recycled rubber? Excessive heat will cause the polymer chains to scorch and lose their inherent elasticity, rendering the material brittle. Conversely, temperatures below this threshold allow residual moisture to remain trapped within the granules, which would destabilize the chemical bond during the blending phase. A system of infrared sensors continuously scans every centimeter of the rotating drum, transmitting data to controllers that adjust the gas burners in real time. But this is just the beginning. One can notice how the dark rubber granules tumble inside the metallic cylinder as the internal blades rotate ceaselessly. Under this controlled heat, the moisture evaporates in invisible plumes, causing the surface of each grain to become chemically active. The equipment gradually transforms the physical state of the material, preparing it like a dry sponge destined to absorb liquid. This activation is essential for the rubber to effectively integrate with the liquid asphalt in the subsequent stage of the production line. The process is only gaining momentum. When the rubber eventually exits the dryer, it is hot, devoid of moisture, and highly reactive to bitumen. At first glance, the fusion of solid rubber and liquid bitumen seems like an impossible mixture, but in reality, this stage functions as a form of modern industrial alchemy. Bitumen is a dense black viscous liquid that serves as the primary adhesive for roadstones. Large-scale tanks store this substance at temperatures ranging from 160 to 190 degrees Celsius. This thermal level exceeds the boiling point of water and rivals the heat of industrial frying oil. It is visible how the substance flows through insulated pipes like a stream of black lava. The process does not end at this stage, as the dry rubber is injected directly into this searing liquid stream within a specialized mixing unit. The material moves further along the production chain to complete its thermal transformation. 20% is the precise proportion of rubber generally required to compose the technical mixture within the reaction tank. Why is such a specific ratio necessary for the production of asphalt rubber? At first glance, the process might resemble simple physical blending, but in reality, it is a complex chemical transformation. Inside the chamber, powerful mechanical agitators rotate at high speeds to create a violent vortex, forcing the two distinct materials into constant collision. The equipment gradually initiates a phenomenon known as swelling during 30 to 60 minutes of intense agitation. One can notice how the rubber particles begin to absorb the light oils contained within the bitumen, causing them to expand and effectively doubling their original physical size. The consistency of the substance undergoes a visible change, thickening from a thin, runny liquid into a robust and gelatinous mass. This specific transformation provides the material with its enhanced properties, where the rubber functions as a network of microscopic shock absorbers embedded directly inside the binder. It is visible how this internal structure makes the finished road surface highly flexible. When a heavy truck passes over the pavement, the entire structure bends slightly under the weight, before returning to its original shape instead of cracking under the pressure. The material successfully resists the intense heat of the sun and the freezing temperatures of winter alike. We are observing the creation of a hybrid material designed to defy the natural process of aging. But this is just the beginning of the logistical challenge. Everything only gets more complicated as the mixture begins to cool, turning thermodynamics into a critical enemy of the process. From the exact moment the substance exits the reaction tank, a race against time begins to preserve the internal heat of the batch. The asphalt rubber is discharged into the beds of dump trucks that have been meticulously preheated to a specific temperature. If the metal surfaces of the vehicle remain cold, the mixture will adhere to the steel-like industrial glue, which would result in the complete destruction of the cargo. 130 to 149 degrees Celsius is the critical temperature range required at the point of discharge. Every single degree lost during the transport phase represents a step toward a potential failure of the entire paving operation. The trucks move at high speed toward the construction site, where the paving crew waits with the precision of a professional racing pit crew. The camera glides along the vibrating finisher, a complex and highly precise machine that receives the steaming black load into its hopper. Its internal steel augers rotate ceaselessly to spread the dark mass with absolute uniformity across the prepared surface. 82 degrees Celsius is the critical thermal threshold that dictates the survival of the structural bond. Why must the compaction process be completed with such aggressive speed? It seems simple to flatten the material at any time, but in reality, if the internal temperature of the mass falls below this specific point of death, the bitumen loses its adhesive properties and will no longer fuse. Compacting cold asphalt results in immediate failure where the surface does not unify, but instead shatters into brittle, disconnected fragments. The screed plate levels the material with millimeter precision across the entire width of the track. One can notice how the thickness is adjusted through digital interfaces, typically maintained between 4 and 8 centimeters, depending on the load requirements. Immediately behind this stage, the heavy compaction rollers begin their synchronized movement. The equipment gradually transitions into a rhythmic sequence of mechanical pressure. Steel drum rollers glide over the steaming mass to smooth the surface into a glass-like plane. Everything only gets more complicated as the secondary rollers with rubber tires enter the line. It is visible how these pneumatic tires knead the roadbed, effectively forcing out trapped air bubbles and sealing the internal structure against moisture penetration. The process is only gaining momentum. If the engineering team executes these maneuvers successfully within the narrow thermal window, the liquid mass transforms into a solid mineral structure in just a few hours. The resulting pavement is then capable of supporting millions of tons of heavy traffic for several decades without structural deformation. But what occurs when this superhighway finally reaches the end of its 20-year service life? At first glance, the worn surface appears to be industrial waste, but in reality, this material possesses a characteristic of near immortality. Asphalt stands as one of the few substances on the planet that can undergo infinite recycling cycles without the loss of its fundamental chemical essence. When the old road begins to show the first signs of deep cracking, it is not discarded or buried in a landfill. The process is simply reversed. Giant milling machines, functioning like massive mechanical predators, tear into the old surface with rotating drums equipped with carbide teeth. One can notice how the equipment gradually grinds down the very road previously described, reducing it to a granular material known as reclaimed asphalt pavement, or RAP. This recovered resource is then fed back into the production cycle to begin the transformation once again. The material is ready to move to the next processing phase without haste. 1,800 rotations per minute is the speed at which impact crushers pulverize old stones and hardened bitumen. Trucks transport the excavated material back to the processing plant for immediate reclamation. Why is this mechanical destruction necessary for the pavement? The crushing action breaks down the aged asphalt into a fine, workable consistency that allows for chemical reintegration. Without this precise pulverization, the recycled components would remain too rigid to bond with new materials. The equipment gradually recharges the mixture by heating the aggregate and introducing specialized rejuvenating agents alongside a calculated volume of fresh asphalt. One can notice how the rubber from discarded tires remains within the infrastructure, circulating through the system and transitioning into a new functional life. It is visible how the end of one road literally becomes the physical foundation for the next. At first glance, the process seems like simple recycling, but in reality, it creates a perfect closed cycle where waste is fundamentally eliminated. The process is only gaining momentum. 10,000 tires per kilometer find a noble purpose beneath the black and silent surface of the modern highway. Engineering has rewritten the conclusion of a story that once began with oceans of old tires, contaminating the environment for 4,000 years. These materials are no longer considered refuse. Instead, they serve as the structural muscle that sustains the movement of the global economy. One can notice that these 1,500 times is the total distance that the electrical cables produced annually could wrap around our entire planet. Why does a thin metal wire, concealed deep within your walls, possess 3 stories high is the exact height reached by the massive hydraulic excavators as they loom over the debris in the quarry? Why is such immense physical power required at this stage? One might assume that standard machinery could handle the task of clearing the earth. But without this brute force, the copper and aluminum would remain trapped in their geological slumber of millions of years, locked away beneath the horizon. One can notice how the excavators move with the hiss of heavy hydraulics, their buckets so expansive that they could lift a standard passenger car without any perceptible effort. The equipment gradually feeds a fleet of mining trucks that function as mechanical monsters across the landscape. Each of these vehicles transports several hundred tons of ore in a single trip. It only looks obvious that these machines are large, but in reality, their scale is difficult to grasp until standing beside them. If a person were to stand next to one of the tires, the rubber wall would be twice as tall as their own height. The process is only gaining momentum. Giant steel machines roar across the mine roads, hauling the raw earth toward the primary crushing stations. It is visible how stones the size of large sofas are pulverized as if they were simple cubes of sugar. The crushers reduce these boulders into smaller, uniform fragments that are then ready to be transported to the refineries. At first glance, this looks like the final step of preparation, but in reality, the material remains nothing more than dirty rock and fine dust. Transition to the next level. To transform this grit into a perfect conductor of energy, the raw material must undergo a severe test of fire. The mechanical brutality of the open-pit mine eventually gives way to the intense thermal environment of the smelter. One can notice how the atmosphere changes as the dirt enters industrial furnaces operating at temperatures that defy the imagination. This is heat sufficient to make even solid steel liquefy and flow. In the specific case of aluminum, the transformation becomes a complex chemical battle conducted via an aqueous medium. The molten material begins its transition toward a new state of refinement. 950 degrees Celsius is the precise temperature at which the chemical bonds of bauxite are forcibly torn apart within electrolytic reduction cells. Why is such an extreme thermal threshold necessary for this specific material? The rock remains stubborn and solid until the heat reaches approximately 1,742 degrees Fahrenheit. But this is just the beginning. It only looks obvious that heat alone would be sufficient, but in reality, currents of colossal intensity are required to complete the separation. One can notice how pure aluminum begins to surrender to the electrical force, detaching from the compound and dripping toward the base of the tank. The equipment gradually collects this liquid, which settles at the bottom in a brilliant silvery layer. It is visible how the molten metal forms a dense, heavy pool that must be handled with mechanical precision. The process is only gaining momentum. For copper, the industrial requirements become even more rigorous and demanding. The raw material is submerged into specialized electrolytic baths, where electricity functions as a microscopic filter. Every individual atom of impurity is systematically stripped away until the metal achieves a purity rating of 99.9%. Because a single particle of foreign matter could trigger a fatal short circuit miles down the line, any deviation from this standard is considered an absolute failure. At first glance, the pouring of this incandescent liquid into steel molds seems like the final step, but in reality, the cooling phase is equally critical. The molten metal cannot be allowed to lose temperature at its own natural pace. Systems of forced cooling actively spray jets of water against the exterior of the molds with a constant rhythmic hiss. The camera glides along the casting line as the outer shell of the metal hardens instantly upon contact with the water. One can notice the contrast as the exterior solidifies into a rigid crust while the internal core remains soft and intensely hot. Everything only gets more complicated as the material transforms into massive, solid ingots. These heavy bars radiate an intense orange-red glow that illuminates the surrounding machinery. Tens of tons of these glowing blocks now sit ready for the next transformation. However, a massive solid ingot of metal cannot transport electricity to residential or industrial systems in its current form. The material reaches the standard ready for the further stage of processing without haste. 8 mm is the precise thickness of the initial metal rod, which serves as the foundation for the transformation of raw steel into structural fiber. Why must a solid industrial ingot be subjected to such extreme mechanical deformation? At first glance, the heavy block seems too rigid for change, but in reality, the application of hundreds of tons of pressure allows the metal to be stretched far beyond its original physical limits. The process is only gaining momentum. The glowing ingot, still vibrating with residual thermal energy, moves steadily into the rolling line. Heavy rollers, constructed from hardened steel alloys, exert massive pressure as they rotate at high speeds to compress the mass. One can notice how the metal reacts to the force, undergoing a rapid change in geometry as the short, thick block is crushed and elongated into a slender rod. The equipment gradually forces the material through successive passes until it reaches the form of a long rebar. But this is just the beginning. The rolling process continues until the rod reaches a diameter of 8 mm. Yet this remains far too thick for the production of modern high-strength cables. It gets more complex further on. To achieve the required thinness, the production enters the wire drawing phase, where engineering precision shifts to a microscopic scale. The metal rods are pulled through a sequential series of specialized openings known as dies, which are frequently crafted from industrial diamonds to withstand the friction. The speed is relentless. One can observe the metal racing through the production line at dozens of kilometers per hour while maintaining its structural integrity. The material is forced to become thinner, longer, and perfectly cylindrical through a sequence of controlled mechanical stresses. From a thick industrial rod, the steel is reduced until it becomes a filament. 1/1000th of an inch is the maximum deviation allowed for the diameter of this wire as it moves through the production line in real time. Why is such extreme precision necessary during the final stages of drawing? While the wire appears perfect to the eye, any microscopic fluctuation would compromise the electrical conductivity and structural integrity of the finished cable. A high-precision laser constantly monitors the surface, and if the sensor detects even a slight variance, the automated system adjusts the tension and speed of the machinery instantaneously. The equipment gradually produces a wire that is bright and polished, possessing a surface as smooth as a mirror. But this is just the beginning. It only looks obvious that the metal is ready for use, but in reality, a hidden structural problem exists within the material. After being pulled, stretched, and forced through industrial diamonds at high velocities, the internal structure of the metal is under immense stress. The atoms are packed into a rigid and brittle configuration that makes the wire fragile. If one were to attempt to bend this wire now, it would snap with a sharp crack like glass. The metal requires a restorative process to regain its utility. Transition to the next level. To heal the internal fractures of the material, it is channeled into specialized annealing chambers. One can notice how these sealed furnaces function as a high-technology environment for exhausted metals. Within these airtight chambers, the oxygen is completely evacuated to ensure that the wire does not rust or develop unsightly stains during the heating cycle. The temperature rises smoothly until it reaches approximately 600 degrees Fahrenheit. This thermal energy is not intense enough to melt the wire, but it provides the exact amount of heat required for the atoms inside the copper or aluminum to relax. Everything only gets more complicated. The crystalline structure of the metal, which was distorted and elongated during the intense drawing process, begins to realign into its natural state. Internal stiffness disappears as the thermal energy permeates the core of the wire. One can notice how the molecular tension evaporates under the steady heat. When the wire eventually exits the other side of the chamber, it looks identical to the naked eye, but it has been fundamentally altered on a microscopic level. It gets more complex further on. Before this thermal treatment, the material was prone to breaking, but now it is exceptionally soft and flexible. The wire can be bent, twisted, or coiled into tight diameters without any fear of structural failure. It is visible how the metal lays in an even layer as it is prepared for the next stage of manufacturing. This transformation is entirely invisible, yet it remains a vital requirement for the production of functional cables. Without this specific thermal psi, no electrical conductor in the world would be able to withstand the physical demands of installation and use. Now that the facility has produced flexible and flawless wires, the process moves toward combining them into a structure stronger than the sum of its individual parts. The process is only gaining momentum. We arrive at one of the most mechanically hypnotic moments of the entire industrial cycle. Tens of individual strands represent the foundation of strength in the process of wire stranding. A single thin filament is inherently fragile and susceptible to snapping under minimal tension. Why merge dozens of these metallic threads into a single entity? If you combine them, you create a metallic rope of incredible structural force that surpasses the sum of its parts. This unified core provides the necessary flexibility for installation while maintaining the load-bearing capacity of a solid bar. The machine responsible for this transformation is a massive industrial unit the size of a railway carriage, loaded with hundreds of coils of shimmering wire. One can notice how the central body of the apparatus, known technically as the cage, begins its rotation. The coils move in perfect circular trajectories, generating a silver vortex in the surrounding air. The process is only gaining momentum. Individual wires are pulled toward a singular central point located at the nose of the machine. At first glance, the intertwining looks like a chaotic blur, but in reality, the strands are twisted over one another with absolute geometric precision. The equipment gradually converges the material into a tight, spiraling formation. Everything only gets more complicated when calculating the technical parameters of the strand. Engineers determine the exact angle of this twist to the fraction of a degree. If the pitch is too tight, the resulting cable becomes excessively rigid and consumes an unnecessary volume of precious metal. If the tension is too loose, the cable will structurally fail and unravel during the installation process. The camera glides along the rotating assembly where the noise manifests as a constant rhythmic hum. Automated sensors monitor the tension levels of every single wire within the bundle. It gets more complex further on. If a single strand, Even one thinner than a human hair should break in the middle of this high-speed rotation. The machine stops its operation instantly. Perfection is the only acceptable output for the system. What emerges from the output side of the nose is no longer a collection of loose filaments. It is a unified conductor, possessing the flexibility of a rope and the tensile strength of a solid steel rod. It is now capable of conducting the massive electrical currents required for modern infrastructure. Transition to the next level. The conductor remains in a hazardous state at this specific stage of production. At first glance, it appears finished, but it lacks the necessary protection for safe operation. If the bare metal were touched while energized, the result would be fatal. The exposed surface requires the immediate application of protective insulation to contain the energy within. Molten polymers and high-pressure extrusion systems are prepared for the next phase. The metallic core is ready to move to the next processing phase without haste. 100% of the metallic conductor surface must be perfectly shielded as it enters the high-speed extrusion line to receive its protective polymer insulation. Why is the precision of this coating so critical for the safety of the power grid? The bare metal core moves with mechanical steadying into the extrusion head, where it will be encased in a seamless protective layer. But the process begins in massive silver silos, rising several stories high, containing thousands of kilograms of raw plastic granules. These small pellets of PVC or specialized polyethylene resemble tiny white or transparent beads stored in a strictly controlled environment. One can notice how powerful vacuum systems suck these granules into a machine that functions like a massive industrial-scale hot glue gun. Inside the extruder, the equipment gradually increases the temperature until the solid plastic beads transform into a viscous and completely homogeneous paste. The bare metal wire passes directly through the geometric center of a precision machined steel head, while the molten plastic is injected around it at high pressure. It is visible how the polymer surrounds the core, a process technically similar to encasing a sausage, but executed with a spatial accuracy measured in micrometers. At first glance, this application seems simple, but in reality, the plastic layer must be perfectly concentric to ensure safety. It gets more complex further on. If the insulation thickness is even slightly thinner on one side than the other, electricity can find a path of least resistance through that weak point, leading to catastrophic system failures or fires. The process is only gaining momentum as the red-hot plastic surface makes contact with the metal core. Immediately following the extrusion head, the cable plunges into a long cooling trough filled with hundreds of liters of cold water. One can notice the immediate thermal shock as the high temperature of the polymer drops rapidly. The plastic hardens instantly, locking its molecular structure into a permanent and perfect shape that will remain stable for decades. But for the heavy-duty cables that run beneath city streets, a single layer of insulation is far from sufficient for long-term survival. These massive conductors receive additional layers of protection, including thick outer sheaths designed to resist chemical erosion, industrial oils, and even the teeth of burrowing rodents. Certain specialized submarine cables are further reinforced with heavy steel armor to withstand the crushing pressures found at the bottom of the deep ocean. The final result is a finished industrial product that appears almost indestructible to the naked eye. But is this apparent durability a physical reality or just a superficial observation? The factory does not rely on luck or assumptions regarding the integrity of the insulation. Instead, engineers will attempt to destroy the cable through rigorous stress tests before a single meter of the product is allowed to leave the facility. This marks the transition from formation to the critical phase of quality assurance and structural verification. 100% of the production must pass through the rigorous environment of the quality control laboratory before a single meter of cable is permitted to leave the factory gates. Why is such extreme scrutiny applied to every batch of finished product? At first glance, the testing seems excessive, but the stakes associated with electrical infrastructure are exceptionally high. A single failure does not merely result in a minor power outage. It can lead to a critical energy loss in a hospital or trigger a catastrophic fire in a high-rise building. High-voltage electricity is discharged through the conductor during the initial electrical assessment. The equipment gradually increases the tension to a level significantly higher than the cable will ever encounter during its operational lifespan in a standard grid. One can notice how sensors monitor for any sign of current leakage or minute weaknesses within the protective insulation layers. The process is only gaining momentum. This procedure functions similarly to overinflating a balloon to its absolute capacity. 60 million kilometers of cables span the globe, forming a massive industrial network that moves $200 billion every single year. Why is such a vast amount of infrastructure hidden from the naked eye within the very walls of modern buildings? It only looks obvious that a wire is a simple combination of plastic and metal, but in reality, every centimeter is a technical survivor of a violent manufacturing cycle. This material began its life through a calculated explosion in a deep copper mine before being subjected to a chemical inferno for purification. The process is only gaining momentum as the metal is drawn through industrial diamonds to reach its final gauge. One can notice how the copper is cured by intense heat and then truncheon twisted in a mechanical vortex to ensure structural integrity. The equipment gradually subjects the strands to testing by both open flame and high-voltage electricity to guarantee safety under load. These cables function as the invisible arteries of modern civilization, maintaining the vital energy flow of every metropolitan center. Without these conductors, the heartbeat of global cities would cease within a single second of failure. It seems simple to flip a light switch, but the journey of that electrical pulse depends on this epic industrial transformation. Australia generates $90 billion by feeding the world, yet the nation currently faces an invisible environmental collapse. One can notice how the fertile topsoil is transforming into clouds of red dust across the horizon. 4 million hectares of productive land die annually, physically lifted and carried away by the wind. Modern technology failed to halt the erosion, but salvation arrived from the most unexpected source found in rotting piles of agricultural waste. But this is just the beginning of a different kind of recovery. Everything only gets more complicated when considering how to stop an entire continent from becoming an absolute desert. At first glance, dirty wool appears to be a useless burden or an industrial byproduct of no value. In reality, these mountains of discarded fiber have become the only effective shield capable of anchoring the soil and preventing total desertification. The process concludes this phase, opening the road to a surprising ecological restoration through industrial waste. 427 million hectares represent the staggering total landmass of the Australian continent. This expanse has functioned for generations as the colossal agricultural engine of the Southern Hemisphere, operating as a relentless food production machine that historically never ceased its momentum. But this is just the beginning. One can notice how, beyond the immediate green horizons, the landscape reveals the physical scars of a long and silent struggle against degradation. Why is the Australian landscape currently losing its battle for stability? It would seem that a land of such scale would be inexhaustible for cultivation. But the country now faces a brutal paradox where its status as an agricultural superpower is undermined by the literal disappearance of the ground beneath its mechanical equipment. Decades of intensive industrial farming have extracted a devastating price from the terrestrial environment. One can notice how soil layers that required several millennia to form have now surrendered more than 60% of their original organic matter. It gets more complex further on. In critical production regions such as New South Wales, the fundamental vitality of the earth has plummeted drastically within a period of only 14 years. Organic carbon, which serves as the physical fuel for soil health, has vanished from the subterranean structure. Without this critical component, the earth loses its natural biological adhesive. It only looks obvious that soil would remain intact, but in reality, the earth stops functioning as a nutrient-rich sponge and transforms into sterile, loose dust. The process is only gaining momentum. When periods of intense drought arrive, the environmental conditions shift toward a state of total collapse. One can notice how the movement of air ceases to carry simple sand and begins to strip away the productive future of the entire nation. 1,800 kilograms is the weight of topsoil removed from every single hectare each year by wind erosion in specific vulnerable areas. The equipment of nature functions like invisible trucks, constantly hauling the concentrated fertility of the landscape and depositing it directly into the depths of the ocean. It is visible how this cycle continues day after day, depleting the geological reserves of the continent. The material continues its migration toward the coast, leaving behind a weakened and fractured substrate. From here, the transformation of the landscape moves into a phase of critical instability that threatens the very foundation of the industrial food chain. 6 million hectares of land now occupy the red zone, officially classified under the status of extreme erosion risk. Why has such a vast territory reached the point of total collapse? It would seem the natural cycles of the continent could endure seasonal shifts, but the reality is far more severe, as 3,200,000 additional hectares are currently disintegrating under the pressures of water degradation. One can notice how the earth cracks, dries, and eventually loses all biological viability. Families in Queensland who have managed the same plots for multiple generations are forced to abandon their homes as the soil fails to retain even a single drop of moisture. Agricultural infrastructure, representing a total value of billions of dollars, vibrates unsteadily upon foundations that are literally turning into fine dust. The process is only gaining momentum. The country required a miracle to stop this environmental hemorrhage, yet the solution emerged from a paradox within another national sector. While the earth suffered from depletion, the domestic wool industry was drowning in its own surplus. It seems simple to keep these two crises separate, but in reality, they are deeply interconnected parts of a technical and economic storm. Australia formerly functioned as a global wool kingdom, where the merino sheep was synonymous with white gold. Annual exports at that time exceeded $4 billion, but the global market dynamics underwent a fundamental shift. One can notice how the demand for raw materials fell sharply, while the international prices for unprocessed wool collapsed entirely. The material that served as a symbol of national wealth transformed into a massive logistical nightmare. Fabricas ceased operations, and traditional trade routes came to a complete standstill. But this is just the beginning. Forecasts for the year 2024 indicate a production drop of 12%. It is visible how the shearing process continues despite the lack of buyers, as the animals do not stop growing their coats. This leads to a grotesque accumulation of organic waste that repeats every single year. The sheer volume of discarded fiber remains stationary in storage facilities as the soil outside continues to erode. Thus, the surplus of one industry sits idle while the neighboring land loses its physical integrity. 200,000 tons of low-quality wool currently accumulate on Australian farms, creating an environmental and logistical bottleneck. This material is not the refined fiber used for high-end garments, but rather short, dirty wool saturated with organic debris. Why do farmers treat this substance as a mere burden rather than a resource? At first glance, the sheer volume of this waste seems insurmountable because the costs of disposal often exceed the value of the material itself. Burning these stockpiles is technically difficult and regulated, while burying them in large quantities is prohibited in many agricultural zones. The material remains stagnant. Giant piles of fibrous matter sit exposed to the elements, rotting under the sun and soaking in the rain. One can notice how the texture degrades as the protein structures weaken over time. It gets more complex further on. Left to decompose naturally, wool is notoriously stubborn and requires between 3 and 5 years to break down completely in the soil. During this slow decay, the weight of the sodden piles increases and the organic decomposition generates a distinct, heavy odor. It seems like a simple problem of waste management, but in reality, it represents a profound metabolic rift in the ecosystem. While the surrounding soil lacks structure and vital nutrients, these mountains of complex proteins are handled as if they were toxic contaminants. This situation created a persistent cycle of economic and environmental loss. Money was diverted into storage solutions for what was essentially garbage, while fertile land nearby suffered from worsening erosion. No logical link seemed to exist between the surplus of waste and the degradation of the earth. Everything only gets more complicated when considering the scale of the neglected land. The process of finding a solution is only gaining momentum. The breakthrough did not originate from the deployment of heavy machinery or industrial-scale incinerators, but rather within the confines of a silent laboratory. Scientists shifted their perspective to analyze residual wool as a biological substrate rather than a textile fiber. What they discovered under the microscope was a sophisticated masterpiece of natural engineering. One can notice how each individual strand of wool is encased in keratin scales. These microscopic structures overlap with the precision of tiles on a roof. However, unlike a traditional roof designed to repel moisture, these biological scales possess a different functional purpose. The equipment gradually reveals the intricate surface geometry of the fiber. This discovery marks the transition to the next level of understanding the raw material's potential. The study of these keratin layers continues to reveal the hidden mechanics of the fiber. The transformation of this waste into a functional agricultural tool moves to the next phase of development. 1 5/10 to 2 times its own weight in water is the volume the wool fiber is capable of retaining as it functions like a series of intelligent gates. This capacity allows the material to absorb a massive amount of moisture from its surroundings. Why does this simple absorption lead to such a profound physical transformation? The liquid does not merely sit within the fiber, but causes the wool to swell significantly. The process is only gaining momentum. This swelling causes the wool to physically change its shape once it is integrated into the earth. One can notice how the expansion of the fibers pushes against the surrounding particles to create something vital for the ecosystem. It creates space in the form of microscopic air pockets. The compacted and suffocating soil typical of the Australian landscape desperately requires this specific type of subsurface aeration to remain viable. It seems simple at first glance, but in reality, the wool offers a passive way to pump oxygen into the ground. It gets more complex further on. This biological mechanism eliminates the need for heavy mechanical plows that often destroy the delicate internal structure of the earth. Initial tests conducted in New South Wales produced results that were scientifically shocking to the observers. Researchers distributed a thin layer of this previously discarded wool over severely degraded soil to measure the impact. The sensors began to register data points that appeared statistically impossible under those environmental conditions. The equipment gradually recorded a 35% drop in surface evaporation, which remains the primary enemy in an arid climate. Water that would normally vaporize into the hot atmosphere was instead trapped deep within the soil profile. One can notice how the moisture remains held in place, guarded securely by the structure of the wool fibers. But this is just the beginning. The true transformation was not just physical, but biological. Where the wool was present, the natural life cycle of the terrain began to return. Between 30 and 50% was the explosive increase in soil microbe density recorded in only a few months of observation. These invisible architects of fertility responded immediately to the new conditions. At first glance, it looked like the wool was only holding water, but in reality, it was fueling an entire underground ecosystem. In test fields located in Queensland, lands that previously resembled solid red concrete began to soften and change their composition. The material is ready to move to the next processing phase without haste. 25 to 40% is the measurable increase in soil moisture retention provided by this technology. Why is this specific range so critical for large-scale agriculture? While the raw material appears to be nothing more than discarded waste, its transformation ensures that water remains accessible to crops even during prolonged droughts. But before reaching the soil, the substance must undergo a radical physical change. At first glance, the raw wool is soft, friable, and shifts in color as it breaks down, signifying the return of biological life to the earth. However, a significant practical obstacle remained for the engineers. Raw, unprocessed fibers cannot simply be scattered across an open field with the expectation of achieving uniform results across hundreds of acres. The material tangles into dense knots, drifts away with the slightest gust of wind, and inevitably clogs the intake valves of seeding machinery. To scale this ecological solution, the unpredictable nature of the wool had to be tamed through precise industrial intervention. This marks the beginning of the industrialization phase. One can notice how mountains of dirty, tangled wool are gathered and fed into high-capacity industrial shredders. Heavy-duty steel blades rotate at high speeds to tear the fibers apart. The equipment gradually reduces the chaotic mass into a coarse, uniform powder that flows steadily through the system. Everything only gets more complicated as the material moves to the next stage of the line. The secret to the final product lies in the application of extreme mechanical force. This shredded wool is forced through precision-engineered steel dies under immense pressure and concentrated heat. It is visible how the friction and compression change the structure of the keratin. The process is only gaining momentum. The output is not a textile or a soft fiber, but a hard, dense, and dry pellet. 100% of the wool's biological potential is now packed into a small, granular form. It only looks obvious that the size is a limitation, But in reality, each granule functions as a biological water battery. When the pellets are buried within the dry earth, they remain in a state of dormancy. But as soon as the irrigation systems are activated or the first raindrops fall, the pellet awakens. The keratin core begins to expand, greedily absorbing moisture and locking it within its internal structure. When the intense Australian sun begins to bake the surrounding landscape, the pellet initiates a reverse process. It releases the stored water slowly, delivering it drop by drop directly to the root systems of the plants. The camera glides along the root zone where the moisture is most needed. This mechanical and biological synergy completely alters the survival rate of the vegetation. The material leaves the production line, transitioning into a calm stage of agricultural application. 90% of the original weight is preserved during the manufacturing process, as 1 ton of residual wool yields 900 kilograms of high-performance pellets. Why does this material allow for significantly reduced irrigation frequency? The answer lies in its physical structure, which retains moisture in the soil, thereby saving precious water resources. One can notice how the pellets gradually decompose over several months, ensuring the slow and constant release of nitrogen, sulfur, and carbon. This is not a synthetic chemical that burns the roots through rapid oxidation. It gets more complex further on. The economic transformation of the industry is as impressive as the biological utility of the product itself. Waste that previously required capital for disposal suddenly possesses significant market value. The market price of this processed material is now 3 times higher than that of the original raw wool. 40 startups emerged in Victoria within a single 12-month period to capitalize on this development. The process is only gaining momentum. It is visible how industrial machinery operates with consistent mechanical force, transforming what was once waste into a biological catalyst. But this revolution did not stop at the Australian border. The technology crossed the ocean and established an unexpected purpose within the United States. In regions like Texas and California, the energy transition is covering desert landscapes with millions of photovoltaic panels. It seems like a simple task to manage these vast fields of glass and silicon. But in reality, these power plants face a persistent natural enemy in the form of uncontrolled vegetation. If the grass grows too high, it creates shadows that block the sun and directly reduce energy production. The traditional solution was a brutal application of labor and chemistry. Teams of workers utilized gasoline-powered brush cutters and toxic herbicides to maintain the grounds. This was expensive, hazardous for the integrity of the equipment, and ecologically disastrous. Stones frequently flew from the mower blades and shattered the glass surfaces of the panels. Fine dust slowly settles over the sensors during such operations, further degrading the efficiency of the array. Transition to the next level. Operators sought a more integrated method to maintain these solar installations without the risks associated with mechanical clearing. The solution appeared when industrial grazing was integrated into the technological maintenance cycle. The process concludes this phase, opening the road to a more sustainable synergy between agriculture and renewable energy. 70% is the reduction rate for chemical herbicides and fertilizers in solar farms that have abandoned traditional machinery. Why did technical engineers decide to replace heavy industrial equipment with biological units? It would seem that automated mowers or chemical treatments would be more efficient for maintaining the grounds. But in reality, mechanical blades often strike stones or sever low-hanging cables, creating maintenance risks that biological grazing completely avoids. The process of solar grazing is gaining momentum. One can notice how sheep navigate precisely beneath the intricate metallic support structures of the solar arrays. They function as high-precision autonomous units, moving through the rows without emitting exhaust gases or kicking up debris that could coat the photovoltaic surfaces. This transition to natural maintenance has caused operational costs to drop by exactly 1/2. It gets more complex further on. Panels provide a massive technical advantage by creating a permanent canopy of shade. This overhead shield protects the animals from direct thermal radiation and simultaneously prevents the rapid evaporation of moisture from the earth. Consequently, the vegetation shielded by these silicone structures grows at a rate 2 to 3 times faster than in open fields. At first glance, this is a simple agricultural side effect, but in reality, it creates a closed-loop energy system. The animals consume the vegetation and immediately convert it into organic fertilizer. This continuous cycle prevents the soil beneath the arrays from becoming a sterile industrial wasteland, allowing the local biodiversity to recover through natural enrichment. Everything only gets more complicated as technology integrates with this ancient practice. Specialized professional grazing teams now manage these industrial sites using sophisticated mapping software. These experts track flock movements with digital precision to ensure that every single square meter of the power plant is processed at the optimal height. The camera glides along the rows where the fusion of high-capacity energy production and ancestral agriculture occurs. The history of natural fibers serves as a technical lesson in humility for modern engineering. Complex solutions were sought to preserve the soil and maintain infrastructure, yet the most efficient mechanism was already integrated into the ecosystem. This stage of the process concludes, opening the road to a more balanced industrial landscape. 45 pounds was the exact weight of the alpha male python known as Loki before his remains were discovered in the deep marshes. Why would an apex predator capable of reaching 5 meters in length be found brutally dismantled in its own habitat? The discovery of the headless carcass, hidden under a shroud of pine needles, suggests that the biological hierarchy of the wetlands is shifting. At first glance, these Burmese pythons appeared to be untouchable kings of the Florida ecosystem. But in reality, the nature of the Everglades has initiated a total systemic counterattack against the invader. The team moved through the dense swamp to document the aftermath of the encounter. It is visible how the heavy body of the predator was torn apart with calculated force. This event serves as a clear signal that the environment is recalibrating its defenses. Everything only gets more complicated when analyzing the origins of this environmental crisis. To understand the mechanics of this biological battlefield, one must examine the engineering of the disaster from its inception. Florida has undergone a radical transformation over the decades, but this is just the beginning of the investigation into the local fauna's response. Two continents illustrate a similar shift in resource management, from the exhausted landscapes of Australia to the high-technology solar fields of Texas. One can notice how a material previously discarded as waste has been repurposed into a primary environmental guardian. Pellets manufactured from raw wool are no longer viewed as mere byproducts of fiber or meat production. They are being utilized to construct a functional shield against the progression of drought. Does the survival of the climate depend on the construction of increasingly massive industrial machinery? The process is only gaining momentum as researchers look toward microscopic tools perfected by natural evolution over millions of years. It seems simple to overlook the utility of natural fibers in an age of synthetic solutions. In reality, the same fleece that provides thermal insulation for sheep has been transformed into armor that regulates soil temperature and moisture. The concept of waste is being redefined as a failure of technical imagination in a world characterized by finite resources. One can notice the equipment distributing these organic pellets across vulnerable terrains to prevent erosion and water loss. The camera glides along the solar arrays where herds now manage the vegetation while simultaneously contributing to the restoration of the Earth. The fleece protects the planet from extreme heat through the same physical properties that once guarded the animal against the cold. Transition to the next level of the narrative requires looking back at how these systems were initially disrupted. The material travels through the production chain to become a tool for global stabilization. This concludes the phase of observing how natural engineering provides the solutions for modern environmental challenges. 30,000 to 300,000 biological units are currently estimated to be operating within the swamp ecosystem. Why did a single weather event trigger such a massive ecological shift? While exotic animals had inhabited this region for decades, the true industrial-scale turning point occurred during the 1992 season. Hurricane Andrew, a storm of Category 5 intensity, functioned as a colossal pneumatic hammer against the structural integrity of reptile breeding facilities. One can notice how the containment failed under the force of the wind. Hundreds of hatchlings were released simultaneously into the vast hydraulic network of the Everglades through this catastrophic breach of security. It seems simple to view this as a localized incident, but in reality, it was the start of a biological takeover. The anatomy of the Burmese python functions as a masterpiece of predatory efficiency designed to process large volumes of organic matter. The process is only gaining momentum. The jaw of this predator is not merely a mouth, but a highly specialized expandable loading system. It possesses the mechanical capability to open to a width of 25 centimeters, matching the diameter of a standard dinner plate. This allows the entry of massive biological loads into the digestive tract. Scientists have documented these organisms consuming entire deer weighing 35 kilograms, a mass that appears to defy the laws of physical displacement. The equipment gradually adapts to the intake. Everything only gets more complicated once the prey is inside the organism. After the ingestion of a colossal load, the python initiates a state of metabolic overproduction that resembles heavy machinery operating at peak capacity. The heart physically expands its volume by 40% to facilitate the pumping of fuel necessary for the energy-intensive breakdown of the meal. Digestive enzymes multiply by a factor of 40, effectively converting the internal organs of the reptile into a chemical furnace. One can notice how the scales stretch as the internal pressure of the meal is processed over several days. The transformation of the material concludes this phase, opening the road to total assimilation. 99% of the opossum population was effectively erased from the map, as this voracious biological mechanism devastated the local ecosystem. The scale of destruction mirrored an industrial facility that consumes every surrounding resource without restraint. Research indicates that in territories dominated by these invaders, raccoon populations plummeted by 90%. America's natural water filtration systems began to collapse under the sheer weight of this predatory pressure. Why did the balance of nature fail so completely against these intruders? At first glance, the battle for the wetlands seemed entirely lost. But in reality, the environment eventually exposed a critical vulnerability in the invaders' biological system. The case of an individual known as Loki changed the entire trajectory of the conflict. Loki was not a typical specimen, but a Judas snake, a healthy, heavy, and powerful male converted into an undercover agent by researchers. Humans equipped him with GPS tracking technology to infiltrate the population, intending for him to lead them directly to the locations of breeding females. One can notice how the strategic use of such technology turns the creature's own instincts against its species. Everything only gets more complicated when the signal unexpectedly stops. Scientists tracked the final coordinates and discovered a scene that defied the standard logic of physical mass and raw strength. The equipment recorded the exact moment the powerful agent was neutralized. The killer was neither a giant bear nor an armed human being. Forensic evidence combined with trail camera footage identified the predator as a bobcat, a wild feline weighing between 10 and 15 kilograms. It is visible how this predator confronts and defeats a monster twice its own weight. This event was not an isolated occurrence, but the catalyst for a tactical insurgency among local species. Ecologists at the Big Cypress National Preserve captured what they categorized as behavioral evolution occurring in real time. The camera glides along the undergrowth where a bobcat was filmed, systematically neutralizing an apex predator near a vital water source. These feline predators have transitioned to a new level of tactical engagement. The process of ecological recalibration continues as the native fauna begins to adapt to the presence of the invaders. 4 meters of length and 50 kilograms of weight define the massive scale of the female python as it confronts a lone lynx. Why would a predator so much smaller engage such a lethal adversary in a direct encounter? A single second of hesitation or one mechanical error in movement would result in immediate death by constriction. The lynx utilizes its superior kinetic agility to evade the striking range and deliver precise counterattacks. But this is just the beginning. One can notice how the lynx systematically unearths the python eggs buried in the substrate. He does not merely consume the contents. The feline crushes the shells and hides the physical remains to ensure no offspring survive. This is a calculated operation of sabotage designed to eliminate the future generation of the biological enemy. It is visible how the local fauna, which previously retreated before the heavy machinery of the pythons, has begun to discover that these biological machines can be bled. The process is only gaining momentum. 7 million years of evolution have armored the American alligators that are now reclaiming their dominance in the murky aquatic zones. These ancient lords of the swamps have begun to intercept the pythons during their expansion through the territory. These are not minor skirmishes, but direct collisions of titans, where the physics of the encounter remain brutal and uncompromising. one can notice the immense force exerted when an alligator closes its mandibles with one of the most powerful bite pressures in the animal kingdom. When the reptile secures its grip on the snake and initiates the high-speed death roll, the resulting torsional force is sufficient to shatter the serpentine spinal column. The bone structure fails with a sharp mechanical sound that echoes through the swamp like a single gunshot. Everything only gets more complicated as the predator-prey dynamic shifts toward total territorial defense. 14% is the verified mortality rate of monitored pythons that end their life cycle inside the armored stomachs of these crocodilians. Tracking data confirms that the apex predators are actively hunting the invaders to restore the previous ecological hierarchy. It gets more complex further on. This interaction represents a zero-sum game where the survival of one species necessitates the absolute removal of the other. The material balance of the swamp ecosystem is resetting as the indigenous predators adapt to the presence of the invasive giants. From here, the transformation moves to the next phase of the environmental conflict without haste. 220 newtons of pressure are exerted by the talons of a great owl as it descends upon its target. Why is the Everglades airspace now considered a lethal exclusion zone for young Burmese pythons? One might assume the threat to these invasive predators is limited to the water, but in reality, the entire ecosystem has mobilized into an active defense system. Birds of prey operate as biological hydraulic presses, using specialized mechanical force to puncture vital organs in a fraction of a second. Precision is the primary weapon for herons, which utilize their elongated beaks as surgical spears to penetrate the skulls of snakes with a single strike. One can notice the efficiency of this aerial assault as it limits the movement of the invaders. But this is just the beginning. Even the heavy black bears of the forest have transitioned into an opportunistic role, utilizing their massive jaw pressure to crush the necks of weakened or injured pythons. The entire biological landscape functions like a massive immune system, systematically identifying and rejecting a foreign virus. The process is only gaining momentum. Despite this coordinated resistance from local fauna, the enemy remains highly adaptable and continues to develop new survival strategies. It seems simple to assume the python is an invincible machine, but in reality, these tropical organisms possess a critical design flaw within their biological operating system. They are strictly thermal-dependent machines that cannot function when external temperatures drop. Specifically, when the environment falls below 10 degrees Celsius, the pythons experience a total physiological collapse. At this threshold, they lose the ability to move or regulate internal functions, leading to mass mortality. Thousands of specimens perished during the extreme winter of 2010 as their bodies succumbed to the cold. The camera glides along the frozen landscape where the snakes remain motionless, unable to adapt to the sudden thermal shift. Everything only gets more complicated as the population attempts to bypass these environmental limitations. Thus, the struggle for dominance within the ecosystem reaches a temporary equilibrium, ending this phase of the biological conflict. 2018 to 2023 marks the timeframe of recent scientific investigations that have dismantled the hope of climate intervention. It was previously assumed that cold northern temperatures would act as a natural barrier against the expansion of invasive reptiles. Why has this environmental safeguard failed so completely? While it seemed the climate would be the primary savior of the ecosystem, biological evolution has instead taken a far more dangerous path through a silent genetic update. Interbreeding has begun between Burmese pythons and Indian pythons. The latter is a cousin species that evolved in territories with legitimate winters, granting it a significantly higher thermal tolerance. This hybridization process combines the massive physical dimensions and known aggression of the Burmese variety with the climatic resilience and superior agility of the Indian python. Scientists now identify the resulting organism as the super python. This biological shift effectively removes the thermal boundary that once shielded the remainder of the North American continent from infestation. One can notice how the genetic landscape is shifting as these traits integrate into the population. Everything only gets more complicated as the invasion progresses. If these specific genetic characteristics become dominant, the geographical front line will no longer remain confined within the borders of Florida. Predictive models now indicate that these super snakes possess the capability to migrate northward into Georgia, Alabama, and even South Carolina. The process is only gaining momentum. The threat is currently updating its biological parameters faster than human defensive structures can be designed or implemented. Passive observation has been forced to evolve into surgical intervention to counter a force of this magnitude. This organized human response is exemplified by the work of Donna Khalil. She does not operate merely as a hunter, but functions as the personification of industrial efficiency applied to environmental conservation. It is visible how the program transitions from reactive measures to systematic elimination under such professional expertise. As the first certified professional hunter in the state elimination program, Khalil has personally extracted over 1,000 pythons from the ecosystem. This industrial-scale removal is a direct reaction to the accelerating hybridization of the species. The extraction of these apex predators continues as the primary method of stabilizing the local biological balance. One woman stands as a primary defender of the ecosystem, operating with the cold precision of a military campaign. Why does she choose to patrol the absolute darkness of the wilderness? While a standard vehicle would fail in this dense terrain, she utilizes a modified Ford F-150 equipped with a custom elevated observation platform. This steel structure, which she engineered herself, provides a necessary tactical advantage by allowing her to look down into the thickest layers of vegetation. But this is just the beginning of a grueling process. One can notice how she scans the environment with high power lights, searching for a specific visual signature. Hunting pythons requires extreme visual processing that differs from any other form of tracking. The human eye has exactly 3 seconds to distinguish the subtle shimmer of a python scale amidst millions of swaying leaves and shifting shadows. It only looks obvious at first glance, but in reality, the confirmation of a target demands an immediate physical response. Once an animal is identified, the hunter has only 1 second to act by leaping from the moving vehicle to engage the creature with their bare hands. No firearms are used in these encounters, as the task relies entirely on raw physical strength and refined technique. The risk remains immense during every engagement. One can notice the map of this ongoing conflict etched into her skin in the form of scars from dozens of bites. These are the marks of razor-sharp teeth left by massive reptiles that fought to defend their lives against her. She describes the sensation of battling a 6-meter python as being equivalent to attempting to subdue a crocodile composed entirely of solid muscle. The salary for this work remains low while the danger levels stay high, yet her determination is unshakable. It gets more complex further on. She actively trains new recruits to ensure the survival of the operation. This instruction involves more than just hunting mechanics. She teaches them to overcome the primal fear inherent in the darkness. Humans have transitioned from being passive spectators to becoming an elite force in this environmental war. However, the mathematical reality of the situation remains unfavorable. The snakes continue to reproduce at an exponential rate that outpaces human intervention. We require a solution capable of operating autonomously 24 hours a day without human supervision. The final move by the scientific community involved the reactivation of a biological tool that had been sidelined for several decades. The eastern indigo snake represents the apex native predator of North America. This creature possesses a natural immunity to the venom of other serpents, making it a critical asset in the struggle. The process is only gaining momentum as these native hunters are reintroduced to the environment. 42 indigo snakes were released into the pine forests of Florida during a historical operation in 2025. Why choose this specific predator to combat the invasive python population? It would seem that a single species could not shift the balance of such a vast ecosystem, but the indigo snake possesses a lightning-fast strike and a specialized appetite for other serpents, making it a natural tactical countermeasure. These biological units are designed for search and destruction. One can notice how they patrol expansive territories in solitude, moving through the underbrush with relentless precision. Their strategic targets are not the giant adult pythons, but rather the juveniles that form the base of the reproductive pyramid. The logic of this intervention is as simple as it is brutal. By eliminating the young, the cycle of reproduction is severed before it can even begin. The indigo snakes swallow their prey alive, effectively neutralizing entire litters before the invasive pythons can grow large enough to threaten the local fauna. It is visible how the equipment of nature, perfected over millennia, functions without the need for human intervention or external power. Everything only gets more complicated as the snakes integrate into the wild. The reintroduction proved to be an immediate tactical success for environmental scientists. It only looks obvious that a predator would survive, but in reality, establishing a stable population in a compromised habitat is a complex challenge. Months after the initial release, remote cameras confirmed that the indigo snakes were successfully reproducing. They have established a self-sustaining population that monitors the environment without salary or rest. The process is only gaining momentum as the natural order is restored. These snakes act as agents that perfectly distinguish between native species and invaders, ensuring that no collateral damage occurs during their hunt. At first glance, the death of a single predator like the python known as Loki might seem like an isolated incident in the mud. In reality, it was the first signal of a massive ecological revolution. The myth of the Burmese python's invincibility has been permanently shattered. The Everglades are no longer a zone of unilateral massacre, where the invasive species reigns without opposition. Each bobcat that crushes a python egg and every alligator that clamps its jaws onto an intruder functions as a critical gear in a growing machine of resistance. One can notice the subgrowth being cleared of invaders as the indigo snakes continue their work. The battle for the Everglades has transformed into a conflict of a very different nature. Automated survival instincts and biological programming have awakened to fight back against the disruption of the ecosystem. This marks the conclusion of a significant phase in the restoration of the Florida wilderness. The material of the living world is reclaiming its territory, transitioning into a phase of renewed stability.